Hello everyone, welcome to my channel IBwontcrushyou, and today we're dealing with quadratic functions from the chapter functions, and we will deal with 8 problems. So let's get started. Problem 1. The quadratic function f(x) equals a times x squared passes through the point to a. And in point A, we have to find the value of the coefficient a. And in order to find a, we simply have to substitute our x, which is 2, and 8, that is y. So fx is the same as y. So simply 8 equals a times 2 squared. So we have 8 equals a times 4, and we can divide both sides by 4. So we have 2 equals a. So a is just 2. B. Determine whether the function is increasing or decreasing for x smaller than 0. So firstly, we can rewrite our full function with a that we already found, so 2x squared. And the simplest way to find whether this function is increasing or decreasing, we can graph it on our GDC. And you see that this is a parabola. And then you can find minimum point, and you can observe that our minimum point is at x0 and y0. So for x's smaller than 0, you can observe that our function is decreasing. So we can write decreasing. In C, we have to sketch the graph of y equals minus fx and describe how it differs from the graph of fx. So this means that we need to put minus in front of our function, so it looks like this, minus 2x squared. And this means that our function is just reflected over the x-axis, and now we can graph it. Your graph has to look like this. You can find the key points by graphing it on your GDC, then gsolve and y calculate or x calculate, and this is our function. And we have to describe how it differs from the graph of fx. So basically our reflection flips our parabola upside down. Problem 2. A quadratic function fx has zeros at x equals minus 3 and x equals 5. The function reaches its maximum value at f1 equals 8. And in A, we have to write the function in factored form. And in order to do this, we have to keep in mind how our factored form of the function looks like. So it is fx equals m, so the gradient. Now in bracket, x minus x1, so our first zero of our function. And in second bracket, the same with the second 0. So fx equals mx, and here we have minus 3, so just plus 3, and here x minus 5, so our second 0 of this function, and this is our function in factored form. In B, we have to find the value of m, so of our gradient. And in order to do this, we can just substitute our maximum value, which is at x1 and y8. So here we have 8 equals m And now 1 plus 3 in a bracket times 1 minus 5. So we can multiply it. 8 equals m times 4 times minus 4. So 8 is equal to m times minus 16. So 8 is equal to minus 16m. And now we can divide both sides by minus 16. So we have minus 8 over 16 equals m. So m is minus half. So this is our gradient. C, rewrite the function in vertex form. And in order to write our function in vertex form, we have to remember formula for the vertex form. So this is y equals m, so our gradient, and in bracket we have x minus p. P is sometimes also denoted as h, and this is squared, plus q. Q is sometimes denoted as k, but it doesn't matter. What matters is that these values are our vertex. So in our case, maximum value. So we can rewrite it. M is minus 1 over 2 because this is our gradient that we already found. And here we have x stays the same, minus p, and this is x from our vertex, so from our maximum value. So this minus 1 squared and plus 8. D, state the axis of symmetry and the coordinates of the vertex. So our axis of symmetry is always when we have our vertex. So in our case, maximum value. So our axis of symmetry is always x equals to something, and we know that our maximum value is at x1. So our x is 1, and coordinates of the vertex, so vertex is maximum or minimum value. We are given maximum value, so our coordinates are 1 and 8. Problem 3. The values of a quadratic function are given in the table, and we have two rows. First row is with x's, and the second one is with y's. And in A, we have to determine the general form fx equals ax squared plus bx plus c that fits the data. So in order to do this, we have to type the values of x and the values of y into our GDC, into statistics or spreadsheet, depends on the GDC that you owe. And the first column or first list is always x, and the second list or column is always y. So you have to type it into your GDC and then choose calculate, then regression, then x squared, and you have values for our quadratic function. So a is 2, b is minus 3, c is 1. So our function is 2x squared minus 3x plus 1. And in B, we have to identify the vertex of the function. So the simplest way to identify the vertex of the function is firstly to graph it in our GDC, and then you can observe that our function has minimum point. So by choosing gsolve, then minimum point, you can find it. So our x is 0.75 and our y is minus 0.125. And then in C, we have to estimate one more value of x for which fx is 0 that is not in the table. So we can find our x value by choosing x calculate, and then we have to enter y value, so we enter 0, and we can observe that this value is 1, but we have already 1 as x in our table that corresponds to our y0, and the second x that also corresponds to y0 is 0.5. So our answer is x 0.5. Problem 4. A parabola has its vertex at 1 and -4 and passes through the point 3, 0. And in A we have to write the function in vertex form. So I already wrote the vertex form, and now we have to substitute our vertex, remembering that P and Q are our coordinates of the vertex. So our function is y equals m, so our gradient. In bracket we have x minus 1 squared and minus 4. In B we have to determine the coefficient m. So we know that our function, our parabola, it passes through the point 3, 0. So simply we need to substitute this point. So 0 equals m, and x is 3. So 3 minus 1 squared minus 4. So 0 equals m. And here we have times 2 squared minus 4. So 0 equals m times 4 minus 4. So 0 equals 4m minus 4. So we can move our negative 4 to the left hand side. So 4 equals 4m, and now divide both sides by 4. So 1 equals m, so our gradient m is 1. C. Find the zeros of the function. So in other words, we have to find the points on our graph where our y is 0. And we can rewrite our function. So 1, and in bracket we have x minus 1 squared minus 4. And now we can rewrite our function in a standard form. So this is x squared minus 2x plus 1 minus 4. So this is x squared minus 2x minus 3. And now we can type it into our GDC into graph, and then draw it, gsolve, and choose root, and we have x equals -1, and the second x is x equals 3. So this is our zeros of the function. Problem 5. Left at x be equal to 2x squared minus 3x plus 1 and the gx minus x plus 4. And in A we have to find the coordinates of the point or points where the graphs intersect. And in order to find the coordinates of these points, our functions, so our function f(x) has to be equal to our function gx. So 2x squared minus 3x plus 1 equals minus x plus 4. And we have two ways of solving it. We can type it into solver. However, you have to be sure that you will get more than one answer, because some GDCs don't give more than one answer, but the safest way is just to type it into our graph, two functions, then draw it, gsolve, and find point of intersection. And in our case, these are minus 0.823 and 4.82, and the second point is 1.82 and 2.18. B. Calculate the area enclosed between the two curves between the points of intersection. So this point is more for HL, because here we have to use our integration to find the area that is enclosed by two curves. And as you can see on your GDC, if you typed it into your graph, so we are looking for the area between these two curves. And we can see that our gx, so our straight line, is above our fx, so above our parabola. So our gx is above our fx. And in order to find our area, we have to write the sign of integration. Here we have to write our x that we are starting from, and here x that we end at, and here, because our gx is above our fx, so gx, and here in a bigger bracket, and minus fx that is below our gx, and here we have to write our integration, the x that we write every time when we integrate something. And we can rewrite our gx like this, because this is our gx from our comments, and this is our fx, and we have to remember that we have to write it in a bracket, because here we have minus, so our minus changes the signs of our numbers, so we have to remember about the brackets. And now, because our integral is definite, we can simply calculate it on our GDC by choosing Run Mathematics, and then we have Math, and then we have sign of integration with the x, and we can write everything as you can observe on the screen, and you will have the result. And if you calculated it correctly, the answer is 6.17, and we aren't given the units, so because this is area, so we have to leave units square. In C, we have to identify the intervals where our function fx is greater than gx. And now we have to go back to our graph, because our fx is parabola, and you have to find where our parabola is greater than our straight line. And we can observe that our parabola intersects at points that we need to write down now, because at those functions we already found their points of intersection. And you can observe from your GDC that from minus infinity to our this x point of intersection to minus 0.823, our parabola is greater than our straight line, and also from our this point of intersection x, so 1.82 to infinity. So this is our answer, where fx is greater than gx. Problem 6. A ski jumper follows a parabolic path modeled by, and we are given a function hx and where x is the horizontal distance in meters and h is the height in meters. And in A, what is the maximum height reached by the jumper? So if this is parabola, so we know that it has a vertex that is a maximum point. So we can find it by taking a formula for x of our vertex. However, we can also use our GDC to graph our parabolic model, so our function hx, and then choose gsolve and maximum point, and you will see that our maximum height maximum height of this jumper is 21 meters. So our we can write that our h is 21 at x 20. B. How far does the jumper travel before landing? So our jumper lands when y or h in our case is equal to 0, because when h is equal to 0, so the height is equal to 0. So h is equal to 0, and we have to find when our h is equal to 0. So we can substitute h as 0 to our function, or we can simply look at our graph and look for root, and when you have your answer, this is, so our x is 40.5 to 3 significant figures, and units, so meters. C. After how many meters does the jumper reach a height of 5 meters? Give both values of x. So the easiest way is to use our GDC, of course, graph, then draw it, then gsolve, and then x calculate. And when we are entering y value, our y is 5, and you can observe that our x is 2.11 meters, and the second x, because our jumper reaches this height 2 times, so our second x is 37.9 to 3 significant figures, and of course units, meters. D. Could a different value of a provide a more realistic model? Justify your answer based on the situation. So our a is minus 0.05, and we have to determine if a different value of a will provide a more realistic model. And obviously, because maybe this model doesn't take into account a resistance, and in real life jumps are not often very symmetric, so they are rather asymmetric. So we can write our answer like this. Yes, maybe air resistance is not taken into account, and in real life jumps are rather asymmetric. Problem 7. The number of daily visitors to a website after a new advertising campaign is modeled by, and we are given a function where Vt is the number of visitors and T is the number of days after the campaign begins. And in A, after how many days was the number of visitors at its peak? So the easiest way is to graph our function on our GDC, and we have to click gsolve and then maximum point, and our x, so t, corresponds to number of days. So when we have our maximum point is 2080 at x, so t 6. So our answer is 6 days. In B, what was the peak number of visitors? So we already found it at our maximum point. So V equals to 2080 visitors. C, after how many days did the number of visitors fall below 1000 again? So here we also use our graph, and we have to click gsolve, then xcalculate, because we are looking for days, because this is question about after how many days. So we're looking for t, so on our GDC this is x, so we are calculating x, so our y value that we need to enter is 1000, because we are looking for the number of days when our number of visitors fall below 1000 again. So this is t equals 12. D, does this model make sense for t greater than 20? Justify your reasoning using context. So firstly, we have to look for the amount of days when our v, so our number of visitors, is equal to 0. And our v is equal to 0 at t equals 14.3. So we know that we don't have any visitors after 14.3 days. So because of that, this model doesn't make any sense for t greater than 20, because our number of visitors fall below 0, and we know the number of visitors cannot be negative. So it doesn't make any sense. And our answer can look like this. It doesn't make sense because the number of visitors cannot be negative. Problem 8. A student collects data about the height of an object thrown vertically, and we have in first row time, and in second row we have height, and in A we have to use our GDC to fit a quadratic model to the data. So we have to type our values into statistics or spreadsheet, depends on your GDC, and then calculate regression x squared, and we have our values. So A is minus 1.54, B is 6.17, and C is 1.23. So our quadratic function is minus 1.54x squared plus 6.17x plus 1.23. And in B, we have to predict when the object reaches maximum height and state the value. So in order to do this, we have to type our function, our quadratic function, into graph, and we have to graph it and then find the maximum value. And if you did everything correctly, our maximum height is 7.41 meters after 2 seconds. C, assess the accuracy and limitations of your model in this real world context. So we can observe from our table as well from our graph that our model fits, we can say, perfectly the data, because we can observe that our table is rather symmetric and our points generally lie on a perfect parabola. So this can be our strength, and our limitation can be that our model assumes that there is no error resistance, and that's enough. And we can write it like this. Strengths: the model fits the data perfectly, the table is symmetric, and the points lie on a perfect parabola. And limitations: the model assumes no error resistance. And that was the last exercise from the topic quadratic functions. And if you found this video useful and helpful, please leave thumbs up, subscribe to my channel, and in case of any questions, feel free to reach me out in comments down below or via my mail that is written in the description of this video. See you!